There are a few types of special ideals that we need to discuss, and so this definition has two of them. We're going to define a principal ideal generated by an element A and also an ideal generated by a bunch of elements. So let's look at a commutative ring R, and we do need commutative ring here for this to make sense. So we have a commutative ring with unity, and we are going to let A1, A2 up through AN just be some ring elements. Then the principal ideal generated by this element A is defined to be the set of all ring multiples of A. So all elements R times A, where R is any element in the ring, not the real, sorry. Just, let me clean that up. Just our ring elements. So you can think about this as multiples of A, but by ring elements. So notice this notation is the same notation that we used for cyclic groups, but it will always be clear what if we are talking about this principal ideal or if we're talking about a cyclic group from the context, because it's not the same. When we had a cyclic group, we just took A and we multiplied it by A, and then we had A squared, A cubed, we had all the multiples, well, the powers basically of A by itself in a cyclic subgroup, or under addition it was A plus A, A plus A plus A, and so on. This is not what we are talking about here. So this principal ideal generated by A, we can take ring elements from the outside of that have nothing to do with A, but then the product of that ring element with A, that's what is in this principal ideal. And similarly, we have the ideal generated by n different elements. So this would be R1A1 plus R2A2 plus and so on, all the way up through RNAN, where these are just ring elements. So R1, R2, all the way through Rn are elements in our ring. So you can think about this as linear combinations of the A's where the coefficients are from the ring R. So let's look at an example. 3Z is a principal ideal of Z. So the one that we saw before is the principal ideal generated by 3. So there's an example right there. You could just think of this set as we'll take any element in our ring Z, multiply it by 3. That gives you a multiple of 3. So 3 is all you need to generate this ideal. Now, in the definition, we are saying these are principal ideals, and then we say what's in these sets. But it's not really a given that these really are ideals. So technically, we need to prove that these two sets that we just defined are in fact ideals. So let's just do it for the first one. Let's show that this principal ideal generated by A, the way it's defined right there, really is an ideal. And that gives us a chance to also practice using the ideal test from the previous video. So let's do that. So let's prove that A is an ideal in R. And so we're going to use the ideal test. And if you go back or if you check your notes, there are 3 things that we need to do. So the first one is non-empty. The second one was that for A, B, and R, A minus B is in A. And then the third one was this absorption property that RA is in A and AR is in A whenever A is in A and R is in R. So those are the things that we need to show. Okay, let's go about it. So first one. Can we find something that is in our principal ideal? How about 0? Since 0 is in the ring, can we show that it's in A, in this principal ideal generated by A? Yeah, we can, because 0 is equal to 0 times A. And, well, so we have a ring element, we have our A, which is just a ring element, and so this again is in our principal ideal. So our principal ideal is non-empty. Okay, so we got the non-empty part. Let's look at the second part. And remember that R is a commutative ring. So multiplication from the left and multiplication from the right are equal to each other because we have commutativity. Okay, so let's take two elements in our principal ideal. Let's call them C and D. Then what can we say about them? What are they? What do they look like? Well, C is equal to A times some ring element, and D is also equal to A times some other, possibly other ring element. So for R1 and R2 in our ring. And here I wanna use the notes. So I'm gonna pretty much write out the solution the way it's in the notes. Here we have multiplication from the right with R1 and R2. In the definition, we had multiplication from the left, and that's what I'm saying. I mean, commutativity, because we have commutativity, it doesn't really matter which way I'm writing it out right here. So let's see. Then what do we do with this? We need to show that C minus D is an element also in our principal ideal. And can we do that? Well, let's see. C was AR1, D was AR2, and since we're in a ring, we have the distributive property, so this is A times R1 minus R2. But R is a ring, so R1 minus R2 is in our ring, and so this is again an element in our principal ideal, because this right here is an element in R, and so that by definition A times that element is an element in our principal ideal. Okay, so much for the second thing. Third condition, absorption. For that, we need to take, again, an element in A. Let's call it C. Let's take C and A. And we need to take any ring element, R. Okay, and so to show is that CR and RC are elements in our principal ideal. So this is what we want to show. Okay. Well, since C is in our principal ideal, so actually I could have, let me fix that. So since C is in our principal ideal, there exists some ring element so that C is equal to that ring element times A. So there exists, let's call it an R prime, since I already used R before, or we already named it something else. So we have an R prime in R such that C is equal to this R prime times A. And we have then that C times R is equal to, well, C is R prime A, and R is just R itself. But because of commutativity, we have that this is R prime R times A, since R is commutative. This is where we need this. And so here again, we have an element in our principal ideal, since R prime R is an element in our ring. And thus, R times C equal to C times R is an element in our principal ideal as well. So, indeed, we wrote it down as a definition, but we can show that this principal ideal really is an ideal.